Light diffraction. Think different. 8. In 1887, German physicist Heinrich Hertz discovered the photoelectric phenomenon. As an ultraviolet light shooting on a metal electrode, it caused electric sparking and generated electric current. In 1905, Albert Einstein did further research on the phenomenon and gave a theory to explain the photoelectric effect. Since light can cause the moving of electrons, people believe that light, like electrons, is also composed of particles. Soon after, people discovered the diffraction phenomenon of light. When light passes through a small hole, it presents a series of ring-like structures with alternating light and dark. When it passes through a slit, it presents a series of stripe-like structures with alternating light and dark. These are very similar to water ripples. Therefore, based on the diffraction phenomenon of light, people proposed that light is a wave. Thomas Young first discovered the double-slit diffraction phenomenon of light. In the figure, CDEF is the diffracted light produced after passing through the double slit. He made a detailed calculation of the fringe spacing and the double slit distance and obtained the frequency of the diffracted light. Since he could not explain why light could form a wavy diffraction image, he proposed that light is composed of waves. Since then, the debate about whether light is composed of particles or waves has continued, and there is no conclusion yet. In order to unify these two views, modern physics defines light as a radiation with electromagnetic properties. In other words, light has the dual properties of waves and particles. However, some phenomena may provide new explanations for the wave-particle duality of light. Phenomenon 1. Both light and electric current have electromagnetic properties. The reason why electric current has electromagnetic property is that the spin axes of all current electrons are in the same direction, making the conductor with current flowing magnetic. It follows Fleming's left-hand rule. The right picture simply illustrates the spin direction of each electron in the current, and the direction of the current magnetic field. Similarly, light also has electromagnetic properties. Light can generate current in a conductor and cause electron transfer reactions. So light has electrical properties. Faraday first discovered that light has magnetism. He conducted an experiment. Two polarizers were placed at a distance. When the two polarizing planes were parallel, light could pass through the two polarizers smoothly. If there is a magnetic field between the two polarizers, the polarized light emitted from the first polarizer will not be able to pass through the second polarizer. Only by twisting the second polarizing plane by a certain angle can the polarized light pass through. Faraday's experiment shows that the polarization direction of light is not only related to the direction of the polarizer crystal structure, but also affected by the magnetic field. How to explain Faraday's polarized light experiment? Assuming that photons have spin, the spin axis is the magnetic moment of the photon. In an ordinary light beam, the photon spin axes are distributed in a series of planes perpendicular to the light beam, pointing in all directions of the plane. Therefore, ordinary light is not magnetic. When light enters a polarizer, the photons have to pass through a series of lattice EM fields. Only photons with spin axes in a certain direction can pass through, and photons with spin axes in other directions will be blocked. Therefore, the spin axis, magnetic moment, of polarized light photons is confined to a certain direction, showing magnetism to the world. When polarized light encounters the second polarizer, if the electromagnetic fields of the two polarizers are in the same direction, the polarized light can easily pass through the second polarizer. However, if the polarized light passes through a magnetic field, the magnetic moment of the photon will be deflected. Therefore, the polarized light cannot pass through the second polarizer. Only when the polarization plane of the second polarizer is twisted to a certain angle and aligned with the direction of the photon's spin magnetic moment can the polarized light pass through. Faraday's experiment showed that light has magnetism, which may be caused by the spin of photons. When all photons spin in the same direction, they become polarized light, show magnetism, and can be affected by magnetic fields. Phenomenon 2. both light and electron beams can produce single-slit diffraction. This is a comparison experiment between electron beam and laser single-slit diffraction. The upper left and lower left fingers are laser single-slit diffraction experiments. The upper right and the 5 lower right figures are electron beam single-slit diffraction experiments. As time goes by, the electrons passing through the single slit gradually accumulate, showing diffraction fringes from left to right on the screen. In the experiment, a large number of photons instantly passed through the slit, and diffraction stripes immediately appeared on the screen. The speed of electrons is very slow, and only a few electrons pass through the slit at first. As time goes by, the number of electrons passing through the slit gradually increases, forming the same diffraction stripes on the screen. Electrons are particles. The experiment shows that particles can also undergo slit diffraction. How to explain the particle diffraction phenomenon through a narrow slit? I.e., the electromagnetic field is widely distributed on the surface of the Earth. It makes everything on the surface of the Earth carry static charges, especially at the tips and edges. 2. The experimental slit has 2 edges. The surface electromagnetic field is very strong, and the 2 slit edges are very close, their electromagnetic fields interfere with each other. 3. The slit edges and polarizers both have electromagnetic fields. In polarizers, the EM field is formed by lattice atoms and electrons throughout the lens, while the EM field of the slit comes from the Earth, only appears on the edge surface. When light passes through a polarizer, each photon is affected by a series of the lattice's EM fields. When light passes through a slit, each photon is affected only momentarily by the edge electromagnetic fields, which depend on their path to the slit edge, their spin frequency, their spin phase, and the angle between their spin axis and the slit edge. Observation from the front of the slit. Top. The spin axes, magnetic moments, of all current electrons are distributed on a plane perpendicular to the direction of the electron beam, and the spin axes of adjacent electrons are parallel to each other. Bottom. The light in front of the slit is the same as the light in front of the polarizer. The photon spin axes are randomly distributed on a plane perpendicular to the light path, and are not related to each other, so normal light does not have a magnetic effect.
After light or electron beam passes through the slit, the spin axis of each photon or electron will be affected by the EM field of the slit, resulting in diffraction. Take light as an example. When photons enter the slit from positions A, B, and C, if their spin magnetic moments are attracted by the slit EM field, they will move forward to positions A1, B1, or C1. If their spin magnetic moments are opposite and repelled by the slit EM field, they will move forward to positions A2, B2, and C2. Similarly, photons at positions D, E, and F will move forward to positions D1, E1, F1 and D2, E2, F2. Photons enter the slit center position O or its vicinity, are equally attracted and repelled by the EM fields on both sides of the slit, and will continue to propagate along the original path. Therefore, after passing through the slit, the light will scatter in different directions. The general diffraction image is related to the following factors: the electromagnetic field strength on both sides of the slit, the forward speed of photons or electrons, the spin speed, the spin phase at the slit, and the angle between the spin axis and the electromagnetic field. Therefore, when the light or electron beam pass through the slit, they form bright and dark stripes on the screen. The particles passing through the central area of the slit are affected almost equally by the EM fields on both sides of the slit. Thus, all particles basically maintain their original path direction. After passing through the slits, they collide and overlap on the screen, leaving wide bright and dark stripes. The particles passing along both sides of the slit are strongly affected by the edge EM field. their path directions change greatly by their original spin direction, spin speed, and spin phase. Therefore, they are dispersed into narrow shadows and dark stripes on the screen. The figures of light diffraction observed from above the slit. The left figure shows the direction of the light path. They are straight lines before the slit, and diverge after passing through the slit, forming diffraction stripes on the screen. The right figure shows the magnetic moment of the photons. Before the slit, they are in a series of planes perpendicular to the light path. After the slit, they are bent to both sides of the slit under the action of the edge electromagnetic field. Diffraction experiment with different slit width. These are the figures of single slit diffraction experiment. The incident light frequency is fixed to red light, and the slit widths are 0.8 mm and 0.4 mm respectively. When the slit width is 0.8 mm, the M field in the center of the slit is weak. The interaction between two edge M fields is weak. Some photons may pass directly through the slit center. Therefore, the central stripe diffraction is not obvious, but it is still wider than the slit itself. When the slit width is 0.4 mm, the M field in the center of the slit is strong. Also, it shows strong interaction between the two edge M fields. Photons are greatly affected and show wider diffraction stripe on the screen. In many light diffraction experiments, the diffraction phenomenon often disappears or reappears, which is very strange. Therefore, it is assumed that the light diffraction is caused by the M field of the Earth's surface at the slit, which is very weak and sensitive. The operation of any other equipment or the change of the position of people or objects nearby may interfere with the experiment and change the results. Since electron beams can also produce single-slit diffraction, it is assumed that the diffraction of light is caused by the charge and spin of the photons. The diffraction result is related to the spin frequency, spin phase, and the angle between the particle spin axis and the edge M field. If the following light diffraction experiment is performed, the hypothesis might be verified. 1. Enhance or change the electromagnetic field at the slit and change the grating width accordingly. 2. Use polarized light of different directions as the incident light. 3. Apply magnetic field between the slit and the screen. Reference. Thanks for watching. Goodbye. November 2024.